And we continue with Chapter 30, dealing with atomic physics. And in this session, we'll talk about X-rays that come from atoms in a special way, fluorescence, phosphorescence, lasers, and a little bit on holography. So we continue with dealing with energy levels in the atom as we go through this material. As X-rays were produced and measured, it was noticed that there is sort of a continuous X-ray spectrum. That's from the bremsstrahlung, the breaking radiation that we've already discussed a little bit. But then there are also these peaks. These peaks are characteristic of the material that the electrons are striking. So if we have copper, we get a set of peaks. If we have nickel, we get a different set of peaks. If we have tungsten, we get a different set of peaks. The peaks are spectral lines of X-rays that are characteristic of the material. So how could we get different frequencies, different wavelengths for different materials? Why might that result? And here's a spectrum with copper as the material, and again the bremsstrahlung. This is a little different scale than the previous slide, but we've got the continuous breaking radiation. As the electron slows down, it's accelerating, decelerating, and emitting X-rays. But then we have these characteristic X-rays where the intensity is quite a bit stronger. Well, what's happening is the incoming electron can knock out an inner electron from the atom. So the incoming electron knocks out an electron in the n=1 orbit, the K shell. An upper electron will drop down into that shell, and in the process there's a change of energy for the electron, so a photon will be emitted. And for the atoms that we're discussing here, copper or nickel or tungsten, there are many protons in the nucleus, and that creates more electrical force. That creates higher energy states. And there is a calculation for rough calculation for the energy state of any n level. And it's basically, again, a negative. All the energy states are negative energy in the atom. But a negative z squared, where z is the number of protons in the nucleus, times 13.6 electron volts divided by n squared, where again n is this principal quantum number that tells us in a crude way where the electron is located, a certain shell. So these are the characteristic X-rays. Which would be the most energetic? The K characteristic X-rays or the L characteristic X-rays? And it is the Ks, because the n=1, that's a lot bigger energy, and bigger energy gap. We're dropping from 2 to 1 than if we drop from 3 to 2. So the K shell electrons dropping into the n=1 K shell, that creates the biggest frequency, the highest energy characteristic X-rays. Of course, X-rays are useful for dental procedures. The dentist can know what condition your teeth are in. A doctor can see what the condition of the lungs are, can image a pacemaker. Security can look inside luggage at the airport and see if there's anything that needs further investigation. There can be computer-controlled X-rays where the X-ray is beamed through in many different directions, and the amount of X-rays that continue on through are recorded, and a computer will make a slice, a three-dimensional image of the patient. Another X-ray here, again, three-dimensional recreation is possible with those X-ray machines. So there's the X-rays. We get these atomic X-rays, the characteristic X-ray, because an upper electron is dropping down to either the n=1 or n=2 level, and the big energy difference there, much greater than the hydrogen atom, but the big energy difference creates a photon in the X-ray spectrum. So now fluorescence, a little bit on fluorescence. The process here is we have ultraviolet light, some people call it a black light, that is directed at either a mushroom or a mineral, and that causes the electrons that receive that ultraviolet light to move up to a higher state, higher energy state. And then as the electron drops back down towards the nucleus, it can drop down in multiple steps. And some of those steps will emit visible light. So we're energizing the atoms with ultraviolet light, and then with our eyes we see this fluorescent light, the wavelengths in the visible part of the spectrum from some smaller energy differences as the electron transitions back towards the nucleus. An insect here glowing with ultraviolet light, different than the minerals. The fluorescent powder in a beaker of water. Chicken cells with a fluorescent dye added. Some minerals over here, and there are different wavelengths of X-ray light that's being directed at these different minerals. And then fish. I don't quite know the purpose of fish having the fluorescence effect, but it can be observed. Phosphorescence is a little different. So there's some toys here, some plastic toys. They've been exposed to visible light, a bright white light, and that light has pumped the electrons to upper energy levels that are metastable. They're long-lasting, so we're storing energy in the atoms, in the electron levels, and then a child or an adult, whoever wants to have some fun, can take this object into a closet, shut the door, and in the dark they'll glow in the dark. So phosphorescence is the slow release of energy from an atom as the electrons stay in the upper energy levels for a significant fraction of an hour or more. And as the electrons then gradually drop back down towards the ground state, towards the nucleus, they emit light in the visible range. The fluorescence is energizing the atom with ultraviolet light and having multiple steps of the electron dropping down towards the nucleus. Phosphorescence is energizing just with visible light, and the atom keeps its energy for a long period of time and will glow in the dark when we take it into the dark. Now to lasers. And we're still talking about energy levels as a key consideration here. For the laser, we have a little different property of light compared to a light bulb. It's more organized, it's directed in a beam, and we'll get to some of its other properties. But again, talking about energy level diagrams is important to understand the laser. So we have an electron here in the ground state, and perhaps just the right wavelength of light hits this atom and delivers this electron to a metastable state. Metastable states, the electron has a long lifetime. A different wavelength of light can bring the electron to a different state. And again, remember the photon here has to have an energy equal to the difference in the energy levels in order for absorption to take place. So we've got the wrong wavelength, the wrong energy for the photon. The atom is transparent for the most part. That's what we'll consider. So we can move the electron in states by having the atom absorb light. The electron absorbs that energy and brings the electron to some upper level. The electrons in the upper levels naturally want to be closer to the nucleus, so they can spontaneously decay down to a lower level and emit a photon in that process. And again, this photon will have a wavelength that matches the energy of the gap in the energy states. If we produce many electrons in the upper level energies and have few electrons in the lower energy levels, then we have what's called a population inversion. That's important for lasers. Population inversion. We want more electrons in the upper state than in the lower state. Can you deduce why that is important? Why do we want more electrons in the upper state? Well, we want the laser to emit light. And to emit light, we need electrons in the upper energy level that'll drop on down. If the electrons are down in this lower level, if one atom emits light, well, that could energize the electron, go to an upper level, and absorb light out of the laser beam. absorb energy out of the laser beam. So we want a population inversion. We want more electrons ready to emit light than there are electrons ready to absorb light. That'll give us the possibility for the laser action. Now in the classroom, we often use a helium-neon laser that has this red light, 632.8 nanometers as output, and it's an interesting process on how this light is produced. The helium, there's more helium in the tube than neon. The helium has collisions with electrons that are energized inside the tube. The electrons collide with the helium and give energy to the helium electrons to these upper metastable states. 2s0, 2s1, if I'm reading that right. In any case, these upper level states that are metastable. So the electron hangs up in here for a significant time. That gives the helium atom time to encounter a neon atom. And as these atoms collide, there is a resonance effect. These energy levels in helium are very close to the energy levels in neon. So the energy from the helium atom gets transferred over, energizes the electrons in the neon to bring them up to these energy levels. And these are metastable states here. There is one of the transitions in the neon from this 3s state down to the 2p state that has an energy gap that produces the 632.8 nanometer light. So the helium-neon laser collisions are important to bring energy to the neon. It turns out it's more efficient than just causing the neon to absorb light and bring the electrons to that higher energy level. So in a laser, if we have this population inversion and we have many electrons ready to go to drop down to a lower level, one of these neon atoms will drop its electron to a lower energy level and emit a photon. This photon perhaps will encounter another energized neon atom, and as it does so, it will encourage the electron to drop down from the upper energy level to the lower energy level and emit a photon. This photon is not absorbed. It's causing the electron in the second atom to drop down. And now we have two photons traveling, and these photons are coherent. They have the same energy, the same wavelength to a very good approximation, and they also are in phase. The peaks are lined with peaks, valleys are lined with valleys, and they are traveling in the same direction. We have coherent light, and some very important characteristics of the laser light. We have basically the same wavelength for the beam, the laser beam, but very much important, we have peaks aligned with peaks, and we have the two photons traveling in the same direction. These two photons encounter a third neon atom where its electron was in an upper state, and now it encourages that electron to decay, and we get a third photon in the group. The three photons reach another energized neon atom. They encourage this electron to drop down, and now we have four photons traveling, then five, and with lots of neon atoms in the tube, we can get a significant number of photons and a significant amount of energy in the laser beam. What helps this is to have mirrors at the two ends of the lasing tube, and there'll be some light that's emitted across the sides of the tube, and that won't get amplified. It won't encourage significant numbers of other neon atoms to emit light. But there's going to be some random atom here that emits a photon along the long axis of the tube, and as it encounters other neon atoms, we get a buildup in the number of photons, and we're moving along the tube parallel to the long axis. We hit the mirror, we bounce back through, and we encourage more neon atoms to emit light, and this light bounces back and forth. Now, the mirrors are not perfect. One of the mirrors has about a 1% transmit rating. So the beam is bouncing back and forth, and about 1% of the light escapes at each bounce. And there's our laser beam coming out. So the laser cavity, a lot of energized neon atoms. They're ready to emit light. The photon traveling past that neon atom will encourage the neon atom to emit light. So So we get stimulated emission as the first photon stimulates the second atom to emit light. And we get the photons traveling peak aligned with peak, as you see in the drawing, traveling in the same direction. They bounce back and forth in the long direction of the tube, but 1% escape at each bounce, giving us our laser beam. So the laser light is coherent. The waves are in phase or traveling in the same direction. And pretty much we're at the same wavelength. There is some Doppler shift, broadening of the wavelength, but we're going to ignore that. So we're going to say we have monochromatic light, one wavelength. The laser beam goes out in a single direction. However, as goes out the tube, that tube has a certain diameter, and we do have some spreading from diffraction at the opening. So as we calculated, the laser beam can spread out to a large size, a few hundred miles on the moon, if we're shining the laser light at the moon with a simple laser. So the lasing action, it is a process that relies on the concept of stimulated emission. The first photon encourages the second atom to emit light. Those two photons encounter a third atom. We build up the strength of the beam, and then one of the end mirrors is partially transmitting, 1% transmitting, and we get the laser beam as a result. Lasers have good applications under trained use. The laser beam, the light can be focused by the cornea and lens of the eye onto the retina. We're getting a focused image back here. And that coherent light, peak aligned with peak, peak aligned with peak, all those peaks getting into a smaller area here can create heating on the retina and kind of weld the retina, repair it back into place where it needs to be anchored down to kind of repair a detached retina. And there's some other uses of laser in the eye that we won't go into. Lasers are also being employed to try to produce fusion, the fusing together of hydrogen nuclei into helium and releasing energy. It would be a safer form of nuclear energy than the fission of uranium. We'll talk more about that in the nucleus chapter. Of course, a laser is used for CDs and DVDs. There are pits and valleys, pits and land. The laser light can reflect off the land, and electronics can detect whether we're getting a 1 or a 0 type reflection and recreate the music or text, whatever might be stored. We can also make holograms. They're a two-dimensional photograph that has a three-dimensional quality about it. And you might see these on a credit card or on currency, on some documents that are trying to be protected. Here's a 50 euro image protected from counterfeiting. Lasers can be used to create simple holograms to do that. How do lasers help create holograms? Well, here we have coherent light. That's important. The peaks are all organized here. A portion of the beam strikes a mirror and goes to the photographic plate where we're going to make the hologram. A piece of film that gets exposed, and the light causes a chemical action in the film. Part of the beam goes to the object, reflects from the object, and comes back to our photographic plate. So we have two beams, and depending on path length here, we're going to have constructive or destructive interference at the photographic plate. And we'll have recorded here an interference pattern that is as if your eye was here on the photographic plate. And now we can again shine coherent light on the hologram, and some holograms can be made so that white light will reproduce the image. But you can look at this hologram and you can move your eye around and you can see around the image, just as if your eye was where that photographic plate was and moving your eye back and forth. So we have constructive and destructive interference here, and we get diffraction occurring on this complicated diffraction grating, the hologram, that was produced when we had constructive and destructive interference along here. Where there was constructive interference, the photographic plate was exposed, where there was destructive interference, there's no developing, no exposure of the photographic plate. And that pattern, that interference pattern, is then recorded in plastic or glass, whatever the film material might be. And later we can look at that and we get a three-dimensional viewing of the object. So that's the mechanism of the hologram. Just kind of interesting here, again, Einstein's name comes up. He worked out the theoretical basis for the laser for the stimulated emission process in 1916. The first working laser was around 1960. And there was one group who built the laser. They had an early award of a patent, but the person who first had the idea, the thoughts about the laser, Gordon Gould, after 28 years of court battles, he was finally awarded the patent rights. Why would someone want to battle for 28 years to be recognized as the inventor of the laser? Well, patent rights come with it the right to license this idea to manufacturers for use. There's a lot of applications of lasers, and it's a very valuable patent to have the patent rights for the laser. So if you do have a good idea, go ahead and submit a patent application. Gordon Gould did not do that. That was a flaw. He should have applied for a patent right away. The other individuals applied for the patent and were awarded initially. Again, after appeal process, Gordon Gould did do something right. He wrote down his ideas and had them notarized with a date and time. And that finally enabled the court system to agree that Gordon Gould invented the laser. So I'm sure you'll have good ideas. Write them down, apply for a patent, get your sketches notarized, make a donation to your favorite university once you start reaping those rewards. So there we are with some more atomic physics, the X-rays coming from electron transitions in atoms that have many protons in the nucleus. Those electron transitions can cause X-rays to be emitted. Fluorescence, where we energize the atom with ultraviolet light, and then the electron makes several steps back towards the nucleus in energy level. Some of those emit visible light and get nice vibrant colors. Some of this is used in advertising, and boxes on the store shelf will have a fluorescent effect to appeal to the eye. Phosphorescence, where the atoms are energized and that energy is stored in the atom to be released later. Over time, it naturally gets released. And we've taken a toy into a dark room. So we have glow-in-the-dark toys, glow-in-the-dark shoes, fun stuff. Laser, we have atoms that have extra electrons in upper levels compared to lower levels, a population inversion. Then one of those atoms spontaneously will have an electron transition that emits light. That photon can encourage a neighboring atom to emit light. The two photons will travel together in the same direction, travel in phase. They're coherent light. And let this happen many times in a laser tube with the light bouncing back and forth, and we get the laser beam that has useful optical properties. Keep reading about that and ask some questions in class.